Let's discuss direct current, DC, and alternating current, AC, today. AC is an electric signal in which the direction of current periodically changes. The principle of AC operation is based on electromagnetic laws. AC is typically generated in power plants, and the AC produced in power plants has constant voltage, current, and frequency. In an AC generator, the rotor, or the rotating part, rotates within a magnetic field to move electrons and generate current. The rotor consists of magnetized components and wire components. As the rotor rotates, the changing magnetic field in the magnetized components induces an electromotive force in the wire components. This generated AC is commonly used for residential and commercial power supply because it is easy to transmit. The frequency of AC refers to the number of cycles or repetitions of the electric signal per second. In many countries, including South Korea, a frequency of 60 Hz is used. The United States and Japan also use 60 Hz, while Europe and most other countries use 50 Hz. Complex numbers are used in electrical engineering, particularly in the context of AC, alternating current, electricity. A complex number is a number that consists of a real part and an imaginary part. In AC circuits, complex numbers are essential for calculating physical quantities such as voltage, current, and impedance. Impedance is defined as the sum of resistance, inductance, and capacitance in an AC circuit and is represented using complex numbers. In AC circuits, both voltage and current are expressed in complex form, allowing us to calculate their relationship using complex multiplication. To do this, it is necessary to understand how to calculate the magnitude and angle of complex numbers. Complex numbers are not limited to AC electricity. They are widely used in various fields such as electromagnetism, signal processing, and communication engineering. Resistance, R, is a physical quantity in electrical circuits that represents the property of limiting the flow of current. It is proportional to the voltage generated when current flows through it, and it can be expressed by the equation V equals IR, voltage equals current x resistance. Resistance is typically measured in ohms, omega, and is applicable in circuits with direct current, DC, where the current remains constant. Impedance, Z, is used to describe the relationship between voltage and current in AC, alternating current, electrical circuits. It encompasses the electrical resistance and reactance of a circuit and helps explain the complex characteristics of an electrical circuit. Impedance is typically represented as the sum of resistance, inductance, L, and capacitance, C. While resistance applies to DC circuits, impedance is necessary for AC circuits, where the current periodically changes direction. Impedance is commonly expressed as a complex number, comprising magnitude, Z, and phase angle, indicating the relationship between voltage and current. Inductance represents the property of a circuit that opposes changes in current flow. It is typically measured in henries, H. Inductors store energy in a magnetic field when current passes through them, and the rate of change of current induces a voltage across the inductor. Capacitance represents the property of a circuit that stores electrical charge. It is typically measured in farads, F. Capacitors consist of two conductive plates separated by an insulating material and can store energy in an electric field. Capacitance depends on factors such as the distance between plates, the area of the plates, and the permittivity of the insulating material. It can be expressed by the equation C equals Q, V. Capacitance equals charge, voltage, where Q represents the stored charge and V is the voltage across the capacitor. Impedance is a crucial concept in electrical circuits as it relates voltage, current, and power calculations. It helps analyze and understand the behavior of circuits in AC systems. Capacitance is typically expressed in units such as picofarads, PF, or microfarads, microF. Both inductance and capacitance represent electrical characteristics that respond to changes in current and voltage in AC electrical circuits. These properties are used to explain circuit behavior and calculate voltage, current, and power in the circuit. Magnetic flux refers to a physical quantity that indicates the amount of magnetic component passing through a magnetic field. It is determined by the intensity of the magnetic field, the area, and the angle involved. Magnetic flux can be understood in terms of flux tubes, which are lines that contain a certain amount of magnetic component passing through a magnetic field. The magnetic flux is proportional to the number of these flux tubes. Magnetic flux gained importance with the discovery that the rate of change of magnetic flux per unit of time is proportional to electromotive force, EMF. This led to the formulation of Faraday's law of electromagnetic induction, which states that the rate of change of magnetic flux is equal to the EMF induced in a circuit. Consequently, magnetic flux is a significant concept in electrical engineering and plays a vital role in the design and operation of electrical devices, electric motors, generators, and other electrical systems.